Very good. It's very bright in my eyes. I cannot see any faces, but thank you for coming to this session. I'm glad to build upon the talk of the previous speaker in considering use cases that ensure greater success for our computational memory, computational storage, and even DPU type efforts. Towards this end, our view is that there is a sea of accelerators. Some will be standalone and some will be embedded in computational memory or computational storage or networking devices. So we want to have common way of programming acceleration because the CTO of Semiconductor Research Corporation, Viktor Zhernov, he has said that logic is free and wants to embed everywhere. So in the future, we expect more and more computational devices, not just concentrated compute like on CPU and GPU. And I will explain the reason for that in a minute. But in terms of the work that I'm describing today, I mentioned that we want to have common interface. So I actually have same presentation. I present to computational storage community, computational memory community, or DPU community. I just changed this slide. So the rest of the implementation and specification of the API is the same. And this is first such effort because programmers in application layer like PyTorch and CUDA, they don't want to do 3 separate interfaces, one for computational memory, one for storage, one for networking. They want to have common view. That is the purpose of this work. And we are targeting similar as Dr. Youngpyo Ju said in previous presentation, data infrastructure such as Spark or Confluent or this type of BigQuery ML, for example, scalable AI such as PyTorch and anything that uses embeddings for inference or learning, media processing, and even also just plain memory nodes that CXL type 3 and type 2 will give us. The notion of success in this effort, which is still in early stages, is that if we are successful, then widely used acceleration libraries such as CUDA library, AMD's ROCm, and Intel's OneAPI or even SYCL will actually embrace this API and provide transparency to frameworks like PyTorch and Spark and Ray. So the intended target of this work is such like acceleration library. The people above that library, the layers of the stack above it, are looking to scale, standardize, and accelerate. The scale they are looking for is maybe represented by benchmarks such as CloudSort, where 10,000 nodes may be working all at once on sorting a very large, sparse, distributed data structure. It might be an HPC style data structure like a multidimensional array or a volumetric grid with a complex stencil, or it might be a more regular tensor or dense data structure, or it might be database tables or very large sparse embeddings. They are looking for cross-vendor and cross-config standardization, so they accelerate or program for acceleration once, and they achieve significant end-to-end acceleration such as 10 to 50x. This is easy to put on this kind of slide. It's in practice very hard. And some of the learnings we have had in the past are that in traditional views such as SNIA and NVMe APIs that we have, you have one host, one device. So when you take task that is running on 10,000 nodes, each host has to constantly proxy for the function that is offloaded to the devices it is managing, which makes communication between devices very hard. And as a result, there is no offload of parallel computation. Whereas in CPU, GPU, this relationship is preserved because GPU accepts parallel offload, or even clusters of GPU take parallel offload. So we are aiming for APIs that look more like NVIDIA Collective Communication Library and look less like SNIA and NVMe interfaces for this reason. And then, similarly, from a provider perspective, the provider lives below the API layer. And so the provider, the first role is, if there is going to be a sea of accelerator, which is thousands of computational memory and storage devices and DPUs, then somebody will have to put all that infrastructure together and set permissions about which compute can see which memory and which hosts see which devices. This is normal in data center. And so when you allocate from sea of accelerators, you want an interface for control plane that is similar to how you talk to Amazon EC2 or you use Terraform or YAML, this type of scripts. So for sea of accelerators in the control plane, you will want similar interface. After that, you want some notion of function and some notion of data. So underneath this integrator who is maintaining topology and providing performance and security, there will be a variety of accelerator vendors who will both absorb the acceleration commands that are meant for them, but also behind that pass on access and offload operations into memory and storage functions that might or might not have compute in them. So for example, previous speaker mentioned SDXI. Copy commands that are issued by SDXI layer may be passed down to an initiator and a target of that copy operation as it is. But additional new commands, such as I'll describe, might be interpreted and then broken up into commands that are meant for specific devices to execute. Like a big operation on large graph may be handed off to each partition of that graph that is executing in a computational storage or computational memory device. Okay? So this is the kind of setup we are assuming. And the reason is that in practice, customers such as hyperscale first-party workloads like the Cosmos data lake at Microsoft, they're already in 10 exabyte range. There are starting to be many multi-hundred petabyte to single-digit to tens of exabyte workloads at large companies that I work with. And a key consideration, like previous speaker mentioned, is that for reasons of power and latency and even exploiting internal device throughput, data gravity is now a key consideration. Many times we want to process data where it is instead of moving it out of device only to throw away most of that data. This is well understood. And there is need for very large end-to-end acceleration, as I said. So I think many people, when they describe this kind of thing, they only think of the memory hierarchy. Actually, because of considerations of data gravity and the simple fact that logic is free and wants to embed everywhere, there is starting to be compute in places other than where bulk of the compute happens. So as we know, the compute hierarchy is fattest, where the memory hierarchy is the thinnest. Okay, so we have very little SRAM and HBM in the world, and we have a lot of flash. But thankfully, there is some compute available near flash, and with CXL introducing all these new tiers of memory hierarchy, like first tier through CXL1 on still within the server on expander, but then with CXL2, we have rack level memory, like pooled memory. With CXL3, hopefully we will get fabric memory. And behind that, we still have existing RDMA fabric that provides some memory semantic, mainly among compute, but they can also provide that among devices. And of course, NVMe has a strong computational storage effort as well. So how do you program these in a consistent way? Requires us to think about common abstractions that might be useful. Pre-CXL, there were no good abstractions that covered everything using a uniform interface. But the CXL type 2 is a very good abstraction for describing functions like that have both memory and accelerator. So we believe it to be a good unifying abstraction. And to that extent, starting with Samsung and now increasingly from other SSD vendors, for example, we are starting to see products that look like CXL memory semantic SSD, which have CXL. We call this accelerator first storage. So first generation computational storage devices and standards from SNIA and NVMe had a storage first architecture. The accelerator was hidden behind NVMe controller. NVMe is poor transport for acceleration because it's not suitable for coherent accelerator, for example. But CXL is great. So now, in these new generation devices, we expect that the accelerator and storage, for example, in a computational storage will flip around, and the CXL personality will be front So you will talk to an accelerator, and there might be a memory hierarchy behind it. Okay? So from that point of view, the gaps that we see in existing work are that the protocols from SNIA and NVMe are command heavy and communication poor. So we're trying to build upon that work by coming up with a very simple theory of operations that has 3 ideas. One is to be allocate from this kind of sea of accelerators. The second is have notion of data set that is not adversely affected from an acceleration point of view if you cache that data, for example, in DRAM in front of storage. In previous generation, when you had separate interface for computational storage and separate for memory, you had to program differently if they cached in the database buffer cache, which was not desirable from customer point of view. And the third thing is, this is explained well in Google's paper, like at ISCA 23, that in order to accelerate nowadays, there has been a lot of progress, and we want to do things like streaming graph launches and not do one function at a time in a non-pipelined fashion. Okay? So the first part, like I said, is very similar to how you do YAML scripts today. You have hosts and DPUs and devices have controllers, and controllers can be endpoints for services. So they can do functions just like hosts can. Hosts can have private fabrics, so a host can be like a simple cluster, or it may have NVLink or NVSwitch behind it, so it can be as complex as a DJX box, for example. Okay? The notion of a data set is that it's a device computable set of objects. And when we looked at best practice for, I will make slides available after the fact, so you don't need to take pictures. Memory is allocated when you do like a new operation or a heap allocation on function entry. That is most of computational computed memory. What we have seen in CXL and pre-CXL far memory is that when people demote memory to far memory tier, they generally pack many cache lines and pages using page classification and create these packed objects. Some packed objects can look like Parquet formats. They have compression and encoding. And some objects can be very computable, like they can be arrow format, where you can compute even on packed format without unpacking it. So this kind of notions of data all the way down to, for example, S3 tier, where you may have to do a heavy HTTP operation to get the data closer to compute where you can work on it. Okay? The entire thing has to be encompassed in the new API because you don't know where data will be. So this API attempts that, and it has 2 kind of simple classification. What can be computed by who? So clearly, when data is in files, it's full of packed objects that are not directly computable. You have to expend effort to make it computable, like you have to unpack it, or you have to map a file, even if it has arrow objects in it. But some data, like allocated objects on host, are computable by that host. Data that has been packed and demoted and then brought up, unpacked into a device memory, it can be operated on that device's compute, like was described in previous presentation. But with CXL and even with RDMA fabric, some memory can be exposed in the fabric and can be subject to things like RDMA read-write or CXL load store. So if something is in exposed memory, it can. So this kind of idea, and combining with the arrow work that previous speaker said, and combining with best practices in acceleration, like not just launching single coroutine or not just launching pipelines against a single function, but to actually offload a graph of functions and to trigger them in a reasonable way with parallelism exposed using best practices from high performance computing, where 10,000 nodes may do an all gather operation, is the new way that the API wants to work. And I want to quickly put up one slide to say that where we are at in this is that we are at roughly version 0.3 through discussions in OCP CMS group. And as DCI group forms, we are looking to work with you all to get this API slowly to version 0.5 by the end of the year, and by version 1 by sometime next year. And so it's a simple AI example that is shown here, where the entire theory of operation comes together at the bottom of the page, that you define a service mesh, which is basically a bunch of subgraph builders against embeddings. You define data, which is a social graph whose embeddings have been sharded across 64 pieces. And you define a function that operates and builds a subgraph. And then you can specify through the dependency structure we have that the ith subgraph and the ith function should be co-located. So in closing, what I will say, I'm done. So in closing, what I will say is that we are on an early version of this API, and we want to work with you on more advanced versions. Thank you for your attention.